Welcome everyone to this Tuesday's seminar. It is a great pleasure to have with us Sayan Choudhury from University of Pittsburgh. And I would like to invite our scientific host, Alexei, to introduce our speaker today. Please, Alexei.
Okay, thanks, Dylan. So, as Dylan has already announced, we have Sayan Choudhury today talking about localized dynamics following quantum quench in a non-integrable system. An example on the sawtooth later. Sayan is currently at the University of Pittsburgh, and previously he did his PhD at Cornell University with Erich Müller, where he was working on Bose-Einstein condensates in and out of equilibrium. He was then working at the University of Purdue, and since 2019 he's at the University of Pittsburgh. And as you can already infer from the title of his talk, his interests center about Bose-Einstein condensates, many-body systems, many-body interacting systems, and out of equilibrium physics. And with this, let's welcome our speaker.
Thank you, Alexei. So I'm going to, as the title of the, I'm going to first start off by thanking you for having me. It's a great pleasure for me to talk about my recent work. So this, as the title suggests, the name is Localized Dynamics Following a Quantum Quench in a Non-Integrable System, an example on the sawtooth ladder. So the reference to the work is given below. It's the work with Rishabh Khare, who is a graduate student at Purdue, and this paper has come out very recently. So since this is the first time I'm interacting with all of you, I just wanted to give you a brief overview of the kind of things that I do. So my work is broadly classified into three themes. The first is quantum quench dynamics. The second is many-body physics of ultra-cold atomic gases. And the third is periodically driven quantum systems. Today, I'm going to talk about the first of these topics, which is quantum quench dynamics. Now, when we think about quench dynamics, especially in terms of isolated quantum systems, then if you think about the fate of isolated quantum systems at long times, the idea with quenches is that you prepare the system in some initial state, which is maybe the ground state of some Hamiltonian, and then you very rapidly change the parameters of that Hamiltonian, and then you let the system evolve. So here, for example, is a cartoon of a experiment that was done in Emanuel Bloch's group. So what they did was they put in cold atoms in an optical lattice in only the odd sites like this, right? So then the initial state is a charge density wave. And then they let the system evolve. And now, depending on the conditions of the experiment, the whole density could have become uniform. So this is what is known as thermalization. So you lose all memory of this initial charge density wave, or you might still retain the memory of the initial memory of the charge density wave if under certain experimental conditions. What are these conditions I'll come to very soon. So this is known as localization. So localization is typically observed in strongly disordered systems. So this kind of initial state memory retention you would see in the presence of strong disorder in general. Thermalization, on the other hand, is typically observed in non-integrable systems. Now, localization story is very old. It started with Phil Anderson's seminal work. But one of the really interesting topics in the past decade for research has been what is known as many-body localization. This is really the interacting version of Anderson localization. So the idea here is that you have a strongly disordered system, and due to this disorder, transport is suppressed even when the system is interacting. And now there have been lots of theories, theoretical works, lots of experiments, and many-body localization has now been characterized as an interacting dynamical phase of matter that is characterized by a lack of ergodicity. Now, since I've been talking about single particle localization, thermalization, and many-body localization, it's good to kind of differentiate the phenomenology of all of these three. How does one distinguish between thermal states, single particle localizing states, and many-body localizing states? Now, there are certain aspects in which single particle localizing states and many-body localizing states are very similar. And these aspects come firstly in terms of transport. So thermal states are conducting, while single particle localizing states and many body localizing states are insulating. In thermal systems, the initial conditions get hidden, while for single particle localizing states and many body localizing states, some initial conditions persist. For thermalizing states, the eigenstate thermalization hypothesis holds, while for both single particle localizing states and many body localizing states, the ETH, which is it fails. One crucial difference between single particle localization and many body localization comes in terms of the entanglement growth. So if for thermal systems, the entanglement grows very fast. It grows like a power law. For single particle localizing systems, there's no entanglement growth at all. For many body localizing states, there is a logarithmic growth of entanglement. A similar thing is dephasing and dissipation. So for thermalizing systems, you get dephasing and dissipation. For single particle localizing states, there is no dissipation or dephasing. In many body localizing states, due to this entanglement growth, you do see it dephasing, but there's no dissipation. So now that we've characterized the difference between these states, I want to talk a little bit about some experiments that were done. And so once many body localization was proposed and studied, several experiments came up to establish the presence of this state. So there were experiments done with trapped ions, in cold atoms, in superconducting quantum processors, and all of these showed that in the presence of strong disorder or in the presence of quasi-periodic, the presence of a quasi-periodic potential, you can get the memory of these initial conditions to be retained. And many body localizations, apart from the fact that it's just interesting from the point of view of the breakdown of statistical mechanics, the many body localization actually has a lot of interesting applications. The most interesting of these is in the stabilization of time crystals. So the idea here was that if you have a periodically driven system, then this periodically driven system generically heats up to infinite temperature. However, in the presence of many body localization, the system does not absorb heat from the drive, and this can stabilize the system. And similar approaches have now been proposed for stabilizing symmetry protected topological phases of matter or other kind of topological phases. Many body localization may also be used in certain quantum engines, or it may even be useful for quantum state transfer. So many body localization is now well established that it's a very interesting dynamical phase of matter, and it can have a lot of applications. So many body localization, at least in one dimension, has been fairly well established. I want to point out a couple of references here, though. These are very recent works which question the stability of many body localization in the thermodynamic limit. I'm not going to go into the details of these references, but at least let's just say that even if we can't for sure say whether many body localization is stable in the thermodynamic limit or not, at least for finite size systems, this has been quite well established. So one question that came about with these discoveries was that can many body localization be observed in models without disorder? So there have been some interesting proposals. The one class of proposals which I find the most intuitive are these two kind of proposals on the left here. So what these authors said was, if you have a system which have two species, one heavy and one light, then the heavy species can provide a kind of quasi-static disorder potential for the light species. So this, but there have been some arguments that actually this kind of localization would actually not be stable. And the only way in which you can stabilize such systems, the many body localized phase in such systems, is to make the heavy species infinitely heavy. There are also proposals to realize many body localization in constrained glass models. And finally, there are proposed, this is a very nice proposal for disorder-free localization, where you have spinless fermions interacting via spins, via spin halves. The model here, I think, is very difficult to realize experimentally, but the idea here is that even though the system is disorder-free, the quench itself generates a kind of a dynamic disorder. So the question is then that, are these the only possibilities? Can you get many-body localization without disorder in some other systems as well? So this has been studied quite well, quite a lot in the past few years. So one thing that I found particularly interesting is this idea of many-body flat band localization. So there were two papers last year, one from Kuno, Orito, and Ichionasi, and the other from your group at Korea. So the idea here is that if you have systems where all bands are flat, in that case, even in the presence of interactions in certain systems, certain kind of interactions and so on, you can get many-body localization and ergodicity breaking. So looking at these works, two questions come to mind. First, can localization persist away from this flat band limit? So in the flat band limit, your single particle eigenstates are also localized. And then what these papers show is that this localization can persist in the presence of interactions. So can this localization persist away from the flat band limit? And the other thing that I wanted to was curious about is, can localization occur for systems where all bands are not flat? So to address these questions, we looked to a paradigmatic model, which is the model of a sawtooth ladder. And what we studied was the dynamics of hardcore bosons on this sawtooth ladder. So this is a schematic representation of the sawtooth ladder. I've written down the Hamiltonian here. Let's go over the terms of this Hamiltonian one by one. So the first term here is just nearest neighbor tunneling. So between sites A and B, okay? The next is these tunneling on just the A rung here, okay? So this next nearest neighbor tunneling. And finally, you have the nearest neighbor interaction. So we wanted to study the dynamics of this. Before we get into the interacting system, let's just take a step back and look at the single particle physics of the system, which itself is quite nice. So in the absence of any interaction, this sawtooth ladder hosts compact localized states of this form, where you have this compact localized state is square root of 2 C dagger AI minus C dagger B I minus 1 minus C dagger BI, so B sub I. So this is something that I have shown here, right? This is kind of a representation of the state. And the ground state of the system is localized below a critical density of 1/4, and then at the critical density of 1/4, the ground state actually just looks like this, the interacting ground state. So this happens when J equals square root of 2 J prime, and this is basically just the flat band condition. Okay, so when you have the flat band condition here, only one of the bands is flat. This is different from, for instance, the Creutz's ladder, where you can have both bands flat. And the sawtooth ladder, I should also mention, is a kind of one-dimensional analog of the Kagome lattice. Now, once the single particle physics, we've looked at the single particle physics. Now we're going to get into the many-body dynamics, and I'm going to tell you the how we studied the many-body quench dynamics. So here we looked to do a numerical experiment, very analogous to the experiment that was done with cold atoms. So we prepare a system in some initial state. In this case, you prepare it in a state where particles are only occupy the left half of the system. Okay, and this is very analogous, as I told you, to a 2D experiment that was done by Emmanuel Bloch. And then you let the system evolve, and then you want to look at the system at late times, and you want to see whether some memory of this initial state is at all retained. So to characterize this, we look at this Loschmidt echo, which is just a return probability or survival probability. And we looked at it for different parameter regimes, but I'm going to just focus on 3 parameters here, and I'll tell you why. So the first thing that we find is when both J over V, which is the J being the nearest neighbor tunneling and J prime being the next nearest neighbor tunneling, when J and J prime are both small, then you can get localization, while whether or not you are in the flat band regime. While for this kind of half filling, even if you're in the flat band regime, when J over V is very large, the system gets delocalized. And what this shows is that indeed localization is possible away from the flat band regime. So we went ahead and decided to characterize kind of the phase diagram of where you get localization and where you don't get localization. So we looked at the average values of the return probability averaged over 1,000 tunneling times. And we find that there is indeed a large region of parameter space where you get a significant enhancement of, you get a significant value of the return probability. What was also interesting from this figure here is that if you look at this region, this graph, this figure, for instance, you find that when J prime over V is negative, there is a much larger region of parameter space where the return probability P of T is significant. So this shows that it looks like there's a significant enhancement of localization when J prime over V is negative. So we went ahead and also looked at the dynamics then when J prime equals J and J prime equals minus J, just to look at how the P of T behaves, just to get some, instead of looking at the average value. And here also it's pretty clear that when J prime over V is negative, there is indeed a significant enhancement of the localization. So since this J prime over V seems like a very important parameter in deciding whether the system would be localized or not, we wanted to get kind of an analytical understanding of why does this phenomena occur. So to do this, we resort to perturbation theory.
Sorry, Sayan, may I ask
yes.
a question? How
yes.
How does it look like if you switch V off completely? How do your echo curves look like?
Oh, the echo curve just goes down very fast for this initial state.
And why would that be so? What do you
Sorry?
mean by go? So can you show again maybe the curves on the previous slide?
Okay. So this for instance, if you look at this curve here, okay.
Yes.
So this is very analogous to what you are going to get when if you switch off V completely, because see here J over V is already pretty large.
And that is why? This is because you have dispersive states, right?
This is because you have dispersive states, exactly.
Okay. And
yes.
I get it. And now you go to non-zero V and you start to see some
localization. That's right.
And yes. What are the remind me again, please? What are the filling factors or filling factors which you use here?
Sorry, what are the what factors?
These are spinless fermions, I think.
These are actually the only difference is that once you have the next nearest neighbor tunneling, right? So when you do the Jordan, then it's not exactly, I mean, it's analogous to spinless fermions, but you also get a phase that comes along. But anyway, that's separate. But yeah, you can also think about these as spinless fermions.
And these numbers which you perform, I mean, if I study spinless fermions, I could vary the filling fraction. How many fermions I put in, and what is the corresponding parameter here in your simulation?
For the filling fraction?
Yeah.
So the filling fraction we have fixed to be 1/2.
1/2 means, roughly speaking, 1 fermion per unit cell. Because you have
yes, exactly. One fermion per unit cell. That is exactly right. Yes. Yes.
How do you distribute? How do you can you say something? How these fermions are distributed in the initial state? So they are sitting all in the left part of your system, correct?
Exactly.
But how are they distributed there in this left part? So, so in the left part of the system, you put actually 2 fermions per. You put 2 fermions on each cell. I mean, you fill it up completely, right?
Yes. Sorry.
You fill it up. You fill the left part up completely. I mean,
completely.
Nothing,
yeah.
Nothing
exactly.
more goes. Okay.
Exactly.
Thank you very much.
Yeah. Precisely. That's right. So. Okay. So this is exactly what you were saying also. So this is our initial state where you're filling up the left half completely. So instead of having 1 fermion between A and B, we have fermions sitting on both A and B sides. Okay. Now, what we wanted to do is, since interactions are very important, we start off almost near the Ising limit of V going to infinity, and then we do perturbation theory around it to get to an analytic structure of the localized eigenstate. And then what we're going to do is we're going to see how well our analytics match with the numerics. Okay, so
Sayan, sorry, there is another question. Dario, please unmute yourself.
Yeah, sorry, just a technical question. I mean, the fact that you are considering hardcore boson means that particles sitting in A and particles sitting in B do commute, right?
Particles sitting in A and particles sitting in B do commute. That's right. Yes.
Okay, so this is the fact that is an hardcore boson instead of a fermion. Am I right? That they anti-commute. Okay. Is it crucial for the physics, the fact that they are hardcore bosons?
So there's a little difference in the sense that if we actually take spinless fermions, so no, I think even if we take spinless fermions, I don't think there should be any difference in the physics. I don't think.
I see.
Yeah.
Okay, so it's not a crucial difference. I see.
It's not a crucial difference. No. I mean, I'll tell you honestly, the reason why we considered hardcore bosons was we're coming from the point of view of a cold atoms experiment. So because they consider bosons, so we thought, let's do bosons. Mm-hmm. But yeah, the physics is really not dependent on whether it's bosons or fermions.
Okay, thank you.
Yeah. So, okay, so then we want to build up this localized eigenstate. So we start off with this state, which is our initial state, and then let's act on it with this J and J prime. So what happens is when you act with J, this B and A, the particle from B can go to A, so you get this state. And when you act with J prime, this particle from A is going to go to A, so you get this state. But now you see, in second order, what's going to happen is the following. In second order, this J here is going to connect this state to this state. Okay, so and again J is also going to connect this state to this state. So what we're doing, what we're saying is that at second order, there are multiple paths to reach these two states, and when J prime over V is negative, what you will notice is that these paths are going to interfere destructively. And now what's happening is that when J prime over V is negative, these paths are interfering destructively and the weights of these states are going down. And now whatever states would come up in higher order in perturbation theory, their weights also go down subsequently because the weights of these are going down. And I'm not going through this calculation here, but in principle, you can write down a path integral and sum up a class of paths, and you can show that this kind of destructive interference of paths continues to higher orders in perturbation theory. But this basic idea that you can have multiple paths that reach a particular state, and these paths interfering destructively when J prime over V is negative, this is really the reason why localization occurs here, and why localization occurs why the localization is significant when J prime over V is negative. To see the validity of this simplistic analytical model, what we do is we write down this form for the localized state, which has just got these three terms. We have phi sub 1, phi sub 2, and phi sub 3, just what we have done in the previous slide. There are, of course, higher order terms, but this is an approximation of the localized eigenstate. And now we look at the overlap of this localized eigenstate with the real numerically obtained eigenstate. Okay, and what you see is the following. There is a large regime, really large regime, going up to say about J over V equals 0.8 almost, where this overlap is almost close to 1. So this really shows that how our analytics compared to the numerics, and also shows why we do get a localized eigenstate for localization for a large parameter regime. Now, of course, we've talked about this Manybody interference, but one simple reason why localization might arise is, of course, due to integrability. So to check whether our model is integrable or not, that's very crucial. So we go ahead and look at the spectral statistics to figure out whether our model is actually integrable or non-integrable. So we look at the distribution of the energy level spacings. And now when J over V and J prime over V is small, the system is near the Ising limit. In that case, the model is integrable. And then in that case, it would follow the Poisson distribution. So you see that this is very close to Poisson when J over V and J prime over V is negative. But as you increase J over V and J prime over V, you see that the system goes from a Poisson distribution to a Wigner-Dyson distribution, which is a characteristic of thermalizing systems. So for instance, when you are at J over V and J prime over V equals 0.4, the system, the spectral statistics look very Wigner-Dysonian. However, this is also a regime where you do get localization. So what we're saying now is the following. We're saying that here, this model can show localization even in a regime where the system's spectral statistics is thermalizing. To get an even more, even more better picture of what's going on throughout phase space, throughout the parameter space, we looked at this, diagnostic of the spectral statistics, which is very often used in the Manybody localization literature. So what you do is you calculate one value, which is this expectation value of R, which is essentially just you do min of Sn, Sn plus 1 and max of S sub n, S sub n plus 1. So you take this is R sub n and then you compute all the R sub n's and then you take the average of it. Now for integrable systems, this expectation value of R is close to 0.39. For non-integrable systems, it's close to 0.53. So, we computed the spectral statistics and we find that by and large, R is close to 0.53 throughout this whole regime, but you do get localization even in these regimes where R is close to 0.53 and the system is thermalizing. So localization is observed even when the Manybody spectrum is thermalizing. So now this is kind of reminiscent of this newly discovered phenomena recently, that something which is very exciting recently, which is this phenomena of quantum Manybody scars. So what you have in Manybody scars is that you prepare the system in some initial state, and then the system is going to show coherent oscillations. Similarly, and this will only happen for certain eigenstates, certain initial states. So what we also see here is that, for typical initial states, you start off the system in some typical initial state, you initialize the system in a typical initial state. For most states, this is going to thermalize, the system is going to thermalize. However, there is this special class of states where you can have Manybody, this kind of a quantum interference that will prevent the system from thermalizing, and you will observe localization. So this is also, we can also think of this as a kind of weak ergodicity breaking. So in some sense, similar in spirit to that of Manybody scars, but the actual phenomena is quite different. Is there a question? Sorry. Okay, no question.
Yeah,
more or less.
Yeah, sorry, more or less. I mean, because you said, so just to understand here, you don't see, because, the typical feature of Manybody scars is that, you have an Hilbert space that somehow produce a fragmentation of several chambers.
That's
and
it.
Also typically you see several eigenstates which are, let's say, at low entanglement and also, let's say, equally spaced in energy. You don't see these features in this system. It's a different phenomena somehow.
It is exactly. So what I'm saying is that it's not at all, it's not the same as scars, because scars, you have these fragmentation and you have these eigenstates which are almost equispaced in energy, have low entanglement. Here it's not exactly like that, but here you do see it's not just this state. I will, if maybe at the end I'll tell you, so there are some other states which can also give you this kind of localization, but here the phenomena is quite different. The origin of the phenomena is quite different, but I'm saying that it's similar in that spirit of where you have thermalization, but a thermalizing system, but there are certain states which
survive. Yeah. Okay, thank you.
Yeah. So, so now that we have, so we started off today by, I started it off by talking about how thermalizing systems are different from single particle localizing systems and many body localizing systems, and what was the difference in their phenomenology and things like that. Now here is something which I thought was quite interesting, that you have localization in a thermalizing system. So it's now interesting to go and see what's happening to the entanglement entropy, right? Because the entanglement entropy is an important diagnostic that distinguishes all of these phenomena, and now somehow this is a system where all these phenomena seem to be mixed up with each other. So let's see what's going on for the entanglement entropy. So we look at the half chain entanglement entropy, and I'll just go through this region here. So when the system thermalizes, this is the figure, this is the graph. So here you see that the entanglement grows very fast. In this localizing regime, what happens is that the entanglement grows roughly up to a time which is 1 over the tunneling time. And this is also seen in the case of many body localization. This is not seen in the case of single particle localization. However, after that, the entanglement entropy actually saturates. The system does not, the entanglement entropy does not grow anymore. So this is very distinct from MBL. I have not shown you times greater than these, but we have looked up to very, very long times. And in MBL, what happens is that if you look up to long times, you'll see that the entanglement entropy actually grows logarithmically. Here, the entanglement entropy actually saturates. This is also, yes. Yes.
Which entropy are you here referring to? So you have the half chain occupied, right?
Yes, it's the half chain.
You measure the entanglement between the two half parts, the two parts of your full system, right?
So it's the half chain, exactly half chain. So it's between the left and the right half. That's the entanglement entropy. Yeah.
Yes, yes. But what I mean is that you start in your initial state, you start with one half of your system being completely empty.
Yes.
And the other one occupied. This is quite different from these MBL studies where you fill the whole system and you yet, or am I getting something wrong? And you measure how some entanglement is progressing.
So not exactly, because even for the MBL studies, so if you look at say MBLs with this kind of spin chains, right? So what they do is in many of these studies, they look at the total spin zero sector. So the total spin zero sector, sum of SZ is 0. So the total spin zero sector is exactly equivalent to this half filling.
Yes, no, I didn't mean that half filling. I meant that you start with one half. Maybe I got that wrong. So your initial state is that half of the system is completely filled. Let's say I prefer to talk about fermions. It's completely filled with fermions, and the other part of the system, the other half is completely empty. So when I think about when I look at entanglement entropy measurements in so to say standard MBL systems, and I translate them into what the initial state tells me about the occupancy of the fermions, I thought that they are more or less equally distributed over the entire system.
Right. So, what you're saying is absolutely right. So, in many of these MBL studies, they look at, for instance, kind of something analogous to the classical nail state almost. So, where you have, just one fermion, no fermion, one fermion, no fermion, and so on. Yes. You're absolutely right. But the argument, which gives it the logarithmic growth, that argument is actually not dependent on how you fill it up. So the idea is just that you will have some there's going to be some kind of dephasing which is going to happen with a characteristic velocity. So in practice, what you're saying is absolutely right. That's what has been done in the literature. But in principle, there is no restriction on the type of initial state for for a fully many-body localized system. It should not depend on there should be no dependence on the initial state. That's the statement. So in that sense, one would expect that the logarithmic growth of entanglement entropy should occur irrespective of which initial state we start from.
Thank you.
Yeah. So in this sense, this feature is distinct. And also just along those lines, I would also want to mention that even in terms of the return probability that we had shown earlier, we've seen that the return probability saturates. But actually for many-body localized systems, there are arguments saying that the return probability should also kind of decay eventually up to a constant, but the decay, there should be a decay which is power law in nature. So that is also related to this growth of entanglement entropy. So what I wanted to say here is that the phenomenology of this localization is also quite distinct from both single particle localization and many-body localization. So finally, since a lot of the inspiration came from studies with cold atoms, I just wanted to mention that there are possible experimental realizations of this sawtooth chain in, say, for in ion traps, where if you map this system to spin half systems, then you can create this in ion traps. But you can also do this using cold atoms in waveguides. There's work done in Rice-Gadway's group where they've realized this kind of sawtooth geometry in momentum space lattices. And there are actually proposals for doing this in an optical lattice as well. So this kind of studies, the verification of our results should be possible in state-of-the-art quantum simulator platforms. And with this, I am already on to my conclusion slide. So here we have demonstrated that hardcore bosons loaded on the sawtooth ladder can exhibit localized dynamics for a wide parameter regime. This localization occurs in a thermalizing many-body system and originates from this many-body interference. And the growth of entanglement entropy in the system is distinct from both single particle localization and MBL. And finally, that our predictions can be verified in state-of-the-art quantum emulator platforms. Since we do have a little bit of time, I'll just go to one small backup slide that I had, which is that we were thinking about what are the kind of states that can actually show localization. So essentially, you can see from this the argument for the many-body interference that you should be able to see localization in any kind of state where you have a large domain of a large domain present, and the domain walls being sufficiently far apart. So even for this state, for the small systems that we could do, even for this state here, this kind of many-body interference argument would hold in a manner analogous to what we have discussed in this talk. And even here, we see that there is a large, you do see localization. But then as the distance between the domains start decreasing, this return probability starts falling faster and faster, and the system starts thermalizing. So for sufficiently large systems, you can get localization as long as your domain walls, in some sense, are sufficiently far apart. So the expectation would be that the number of such initial states or the number of such localized eigenstates would generally increase linearly with the size of the system. So it would still remain intensively large. And with this, I also wanted to thank you all for your attention. I think I finished well within time, so lots of time for questions.
Yes, thank you, Sayan, for this wonderful talk. Let's thank Sayan. Questions, please. Dario.
Yeah, do you have some, let's say, hints or preliminary results or whatever, how stable is this picture when you start to turn on interactions? Because, I mean, it looks like that it depends, how can I say, it depends strongly on the, let's say, on the initial flatband physics that you have. So I'm wondering how much it is stable when you turn on interaction.
I mean, I did tell you, right, that the we can see this localization irrespective of whether or not we have a flat band, right? So let's just go back to the first figure. Let's just go to this figure here. So you see that irrespective of whether or not you have a flat band, the interactions is really the crucial thing here. So the interactions between the nearest neighbor interactions, that is what is giving this localization. If this interaction was present, then because here you don't have all the bands flat, right? You will always have a dispersive band. So here it's not so dependent on the flat band physics. It's more dependent actually on the presence of the interaction.
So, I mean, if you say that, I'm wondering if, because, you know, in the Manybody scarce literature recently, not recently, actually it's already quite long, but I mean, in the recent, let's say quite recently, people started to, you know, for example, when you take the PXP model, you have these revivals for the, let's say, the mixed states,
yes,
which are good, but I mean, they decay in time. And for example, for the Z3 states, they decay very fast, but then you can adjust a little bit the interaction. You remember, you can add an additional interaction that somehow, I mean, cure the broken Lie algebra that support the scarce states, and you can, I mean, increase the quality of the revival, and so the Manybody scarce quite a lot. So I was wondering if also in this case, you can adjust a little bit the interaction and promote, let's say, the domain wall situation that decay quite fast can be promoted and be more stable in time.
That's a very good point. I think that is possible. That is so essentially what you want is that you want this kind of destructive interference mechanism to hold. So essentially, if you do increase the strength of the interaction, then even if the domain walls come closer and closer, it should be possible to you know, still retain the localization. Yeah, I mean that this is a very, very good point, and you're absolutely on spot. So that is definitely possible. Here, the whole point is that I mean, why I have talked about the one domain wall state in some sense is because this is the state for which the localization is seen for the maximum parameter regime.
Okay.
Right. So this is in some sense the best initial state to start off with to see the localization. But for the others, yes, you can, by controlling the interactions, it should be possible to, you know, promote the localization and make it stable for, you know, for longer times. Yes.
And do you believe? Then I shut up. I mean, do you believe there is because, you know, the analytical argument that you presented is somehow similar to the, let's say, forward scattering approximation that people use in the Manybody scarce. I was wondering if also in your case because, you know, in the Manybody scarce there is a parallel argument built out, let's say, using Lie algebra, broken Lie algebra arguments and so on. I'm wondering if this language can be introduced also in your setup and you can study in that way.
I would not discount it, but at the same time, while I'm more familiar with the FSA, the forward scattering approximation, I am not, you know, I know of this Lie algebra thing, but I have not really studied it in details. So, you know, I should not make a comment which is not, yeah, I've not really thought about it, but I think, yeah, it's a good point to think about, definitely. So, yeah, I will definitely be happy to look it up and see whether, you know, something can be done along those lines. Yeah.
Okay.
Thank you.
Thank you.
Okay, we have a question from Sergey.
Yeah, thank you for the very interesting talk, Sayan.
Thank you.
Let's just stay on this slide here. So
Yes.
You advocate, so when B is equal to 0 for the single particle problem, so to say, or for the many-body system in the action of interactions, you see immediate delocalization, and this is because you're because at the boundary you have some overlap, because you have these extended states essentially, which just run away. And
that's right.
now you switch on some small interaction, some weak interaction, and you advocate that you get localization. Is there a transition at some finite but small v, or what can you say about that?
Oh, yes, yes. The transition would definitely be at a finite. It's not at infinitesimally small v. It's a definite. It's actually the transition is close to when j over v is close to 1. So and it depends on the initial state, right? So.
Well, here in the curves you show j over v is 0.3. So this is like this is not 1 at least. Let's say this is
No, not this. But let's say this is a, if you look at this thing here, which is where the this is also a good place to look at where the eigenstate is localized. So as long as j over v is close to even 0.8, okay, you see this, the numerical eigenstate and the analytical eigenstate. Because the analytical eigenstate here is also something which is it's an area law eigenstate. This is also a localized eigenstate. So this j over v here is 0.8, but the transition is definitely going to happen at a finite v, and what's going to happen is
Sure. Sorry to interrupt. But in the previous figure, you showed the result at 0.3, at minus j over v equals 0.3.
That's right. That's right.
I thought that the data indicate a localization.
That's right. That's right. It does. J over v is 0.3. That there there it is indeed localized.
Right.
Right.
Yeah. So what happens then at 1? At j over v of the order of 1?
So j over v of the order of 1 is, you get the p of t comes down somewhere close to this.
So at even larger v, you get again delocalization.
No. J over, so this j over v. Okay. So j over v is 0.3. That means that v is quite large, right?
Yes. Well, yes.
What happens is that as you decrease v,
yes,
right? So this p of t is going to keep decreasing.
I see.
Yeah.
Okay. So I got it. And so the crossover transition is roughly at a value of -1. That's what it is.
That is exactly it. Yes.
Okay. And why -1?
So this can be sort of seen from this this expression for the this j prime over v plus j squared over v squared, right? So essentially, you want this j squared over v squared to be of the same order as j prime over v. So if we take j to be of the same order as j prime, one of the things is, of course, here there are two parameters, j and j prime. But if we take j to be of the same order as j prime, then this is going to be this argument would say that j over v should be the same order as j prime over v, and so that okay, so this is a very good question actually. So this argument only says that j over v should be of the same order as j prime over v, but this argument is also perturbative, so we do not actually expect it to hold to j over v equals 1. I actually don't have a very good answer to your question. Sorry. So the only thing I can say is that j over v and j prime over v should be kind of similar, but and j prime over v should be negative. But to get the actual value, it's difficult from this analytical model. I was just basing it off the numerics at this point.
For these simulations, I guess you kept the j and j prime fixed and carried on the correct?
That's right.
Can you show again, please, the single particle spectrum and the values of j and j prime, which we used, and the spectrum which follows from that for the single particle?
The single particle. Wait. So let's just see. Oh no, this is just j. This is just when the flat band condition is met. But you wanted to see how the single particle spectrum depends on j and j prime.
Well, no. I guess I want to see that. So this is what you choose. J is square root of 2 times J prime, right? And J prime is something, I don't know, the order of 1, I guess. I don't know what you use.
Yeah. So we just fix one of these to be a the standard energy unit. So let's just fix J to be 1.
Right. Then we see that the bandwidth in this case is in units of J is 4 of the dispersive band.
Sorry, I didn't hear that.
I'll say your picture shows that the bandwidth of the dispersive band is equal to 4.
Yeah. That's right. That's right.
And the gap between the dispersive and the flat band is roughly 2 or exactly 2. Probably.
Yeah. Roughly 2.
Right.
2. Yeah, 2.
So now the question is, what is the important thing? Is it the gap, or is it the bandwidth, or is it both? You could, in principle, try to tune your the sawtooth ladder in such a way that you increase that you change the gap compared to the bandwidth, and then you could try to see whether your transition point B floats at all or not, or so trying to get an idea of what you have to compare, so to say.
Oh, right. So okay, so not that I have a figure for it, but if we say we fix one of these units, and then we can change the other to change the band gap. So then we can change the other to change the band gap, and in that case we should be it will depend then on the value of J over V, because when J over V is small, we should be able to get this when J over V is small, we should be able to get localization, and when J over V is large, it will be delocalized. But I mean, in principle, we can indeed change the band gap and see how the localization behaves with that. But really, what I wanted to drive in here was the fact that in the single particle limit, due to the presence of this dispersive band, we do not have localization. However, in the presence of interactions, you can get to the localization. So yeah.
Okay, we have a further question by Sungjong. Sungjong, please unmute yourself.
I'd like to know whether there's any size effect in your simulation. It seems that your simulation is not infinite, right?
No, of course not. Yeah, it's just up to maximum up to 14 sites.
Right.
Yeah.
So is there any size dependence on the ratio J over V? Like
so there are two places where we looked at the size dependence. So the first is we looked at the size dependence on the P of T. Okay, I don't have the figure here, but I'll tell you. So if you look at this P of T and you look at the value where this saturation is happening, we looked at the size dependence of this value to check whether there is any size dependence. There is not any size dependence. Also, we looked at how well the analytics and the numerics match, and if there is any size dependence there. There is no size dependence there. Finally, what we did was we looked at kind of a localization lifetime. So because this is a finite size system, eventually this P of T has to go down to 0. So because there are going to be other states that are going to come up. So we looked at this lifetime, which is, we denote this as T star, and we looked at it as a function of this system size L. And we find that this lifetime increases almost, we have just 4 data points, but it seems to increase almost exponentially with the system size. If we had more data points, then that would be analogous to what is seen in Manybody localization, because even there, the localization lifetime generally increases exponentially with the system size.
Okay.
So these are the dependencies on the lifetime. Yeah. But yeah, you wanted to ask some other different dependence on the lifetime?
I just wanted to know whether there's any size effect in your
There
system.
seems to be none. It seems quite robust.
Okay. Yeah. Thank you.
Yeah, sure.
Okay, we have another question by Nana. Nana, please unmute yourself.
Okay, excuse me. So quench dynamics is very interesting topic. So I'm just trying to understand what's the effect of the quench or the dynamics in single particle first, in single particle problem first, then the Manybody localization. I think. So could you please give some comments?
For the single particle part?
Yeah, without this Manybody localization, what's the effect of quench or the dynamics for the system?
Okay, so for the single particle part, what's happening is that you do have these compact localized states in the flat band regime, right? Which is the compact localized states look like this. This
Yes.
1/2 square root of 2. So then what's going to happen is, firstly, as long as if you start off with a, in any of these, if you initialize the system in any of these, in this kind of localized state, then there's not going to be there's no dispersion, and so you're going to indeed see localization. And also, as I mentioned, that as a consequence of this kind of compact localized states being present, if you look at the ground state of the system below a critical density of 1/4, the ground state essentially is going to look like just like this. The ground state is also localized.
I
So
see.
Yes.
So does this quench? I mean, so there are several type of quench, right? For example, there are fast quench or slow quench. For example, slow means that the quench depends on the time. The quench is changing by time or not? Is a constant?
So so for this quench, the quench that we considered was just an infinitely fast quench. So essentially, you just prepare the system in some initial state. But yeah, I mean, in principle, one can also do ramping up the parameters at a certain speed.
I see.
Yeah. So in principle, you can.
I see. So does it depend on? So it means this quench stuff also very closely depends on this initial states, right? For example, the CLS, right?
Yes. Yeah.
So what happens if the initial condition is not CLS?
So for us, the initial condition is actually not CLS.
Not CLS.
Yes. The initial condition is actually not CLS. So if you actually start off with the initial condition of CLS, I've not shown this here, but if you actually started off with this initial condition of CLS, then you do see localized dynamics throughout. So I mean, as long as you have this flat band condition. But if you are away from this initial condition of CLS, okay, which is exactly what we have, then the system gets delocalized even if you're in the flat band.
I see.
Yeah.
So actually for me, so sorry, it's a very stupid question. So usually for me it's like CLS. So localization in the dynamics behavior. I mean this dynamics. So always corresponding to CLS as initial states, right? But in this story, I mean you told me that it's not CLS. So what's the special?
Okay, so what we wanted to say is that even though you are not starting off with a CLS, you can still get localization, right? So in some sense, see, if you start off with CLS and from there, so what's been already shown, right? From once that's shown already from your group and the group here at Korea, also the other group at Japan, that they have shown that if you start off, with this kind of totally flat band systems, then you can get Manybody localization. Here, what you're saying is that you can get localization even if you start off with a non-CLS state. And so the origin of this localization is very different from the CLS.
I see. So it means without CLS initial initial condition, we can also get localization, right? I mean, so yes, you are right. So does this quench position also matters?
Quench
Position. Also, for example, could you please go to the quench process? There's a slides, right? The quench.
For the quench, I'm sorry that there's some.
So there's slides. I mean, you have a slide which tells how does the quench happens, right?
Yeah, like this, right?
Yeah. Could you please give? I actually I may know something. I didn't understand this point. So could you please give this for further explanations? I mean, so the before part and the after part, right?
Yeah.
So yeah, I was lost actually. Could you please just give some comment?
So the quench protocol, what we did was that you are starting off with all the particles on the left half of the chain.
Yes.
Right? And then you let the system evolve, and then you look at the fate of this chain at long times.
Yes.
So that's the quench protocol. So when you're starting off with just one initial state, so then what does it typically mean? It typically means that this was the ground state of some Hamiltonian, this initial state, which is not the which is not a sawtooth Hamiltonian, right? But is the ground state of Hamiltonian, and then we have very rapidly changed the parameters to that of the sawtooth Hamiltonian. Okay, and then we want to see how the system evolves. That's the quench.
Oh yeah. Can I say so? So for example, you have a bosons or you have a particle that at the t equals 0 this time. So it moves, it travels it travels along this chain, right? So at some point, I mean, after it travels sometimes, and then you give it a quench, right? It means.
Right.
So, yeah, actually what I was asking just now is that does this quench dynamics and everything formally, all this story depends on this quench position or not? Yeah, this is exactly what I was asking.
Okay. Yeah, so it does. So as I told you, let's just get back to this final slide. So there are only certain initial states which are going to give you this kind of localization. So essentially you get localization only for states in which you kind of have these domain walls which are separated by large distances much larger than the localization length. What's going to happen is that if domain walls come closer and closer, you start losing the localization. So you're only going to get for certain states. Yes.
I see. Thank you. Oh, okay. Also, okay. Can I go back to the question before? So, for example, you told me that this here we can get localization without CLS as an initial condition, right? So, I think then some other parameters should satisfy some special condition, right? For example, some critical condition, right?
So it's more like a.
Otherwise, I mean, localization cannot happen with any parameters, right?
No. Localization cannot
happen
without
disorder. I mean, without this.
Yeah. So essentially, this is the. Let me just show you the phase diagram in some sense. So what I'm saying is that the localization is indeed, it depends on the. So it's more like a crossover that's going on. Okay, and you want your J prime over V. The localization is significant when J prime over V is negative in this model, and also you kind of, from this numerics, what we find is that J prime over V and J over V, both of these have to be kind of less than order of 1, because otherwise because you are not starting with a CLS, right? So your system is going to become delocalized. Okay, so only when your J prime over V and J over V is less than 1, in that case you indeed end up getting localization.
I see. Thank you very much. Very interesting.
Thank you.
Okay, are there any further questions? I saw some people were having problems with raising hands. So if somebody has question and cannot raise hands, just unmute yourself and ask now. Okay, I guess everyone is happy. So in this case, let us thank Sayan again for this wonderful talk.
Thank you.
Actually, there's a question by, oh, there was just a question by Alexei. Very funny.
Oh,
Alexei,
okay.
It's
you raised
okay.
the hand. What?
Well, I will ask later. That's okay.
Well, maybe you can at least share with us how do you raise a hand if you are a co-host. I was never able to do that. Where is this?
There's still a button raise hand.
Where is it hidden? In the reactions part, in the bottom, or where?
I think it really depends. I mean, from my experience, it changes from interface to interface. On Android, there's this 3-dot thing that you can click, and then you get raise hand stuff.
Anyway. Okay, guys.
Okay, so I mean, we can do the question now since we're still live on YouTube, so that our audience on YouTube can also hear the question, maybe.
Okay, well, basically, my question is pretty generic. So, Sayan, what do you think are the conditions to get this kind of, I would still call it quantum scars, because to me, any non-thermalizing state in the in the set of thermalizing one is a scar. So what are the generic conditions you need to get? Essentially, here you looked at the sawtooth lattice, but I had the impression that the presence of the flat band didn't really play such a crucial role.
It didn't.
Even though you had one. So my guess is you need some sort of frustrating geometry, or is there anything else? So what would be the ingredients you need in a generic model to get this sort of behavior?
Right.
Say if you take a square lattice, which typically people think is not frustrating, what would you need to add to the Hamiltonian to get this kind of localization?
Right. So definitely, I think one of the big takeaways is that if you add kinetic frustration, which is exactly what you have here, so that kind of kinetic frustration can lead to localization or even lead to scars for that matter. So, so yes, so that would be generally something where even for say something like a square lattice, if you can add some next nearest neighbor tunneling terms, right? Go beyond just nearest neighbor, add a next nearest neighbor tunneling term, and make this J prime over V negative. There is nothing so special about the sawtooth lattice for that matter. So I would say that even for a square lattice, there is nothing really stopping you from getting localization, even in that case. So yeah, so adding some kind of next nearest neighbor tunneling, with something which gives you some type of frustration, effective frustration. Yeah.
Okay. Yeah, and then a related question. So you were looking at half filling. What will happen if you go away from half filling?
Right. So even what we saw in general is that we also looked at quarter filling, and so I mean the qualitative story remains similar. That even for quarter filling, there is a large region of parameter space where the system is thermalizing, but this kind of J prime over V being negative can lead to localization. So this kind of the interference argument that I have given, that argument is pretty generic. It actually does not depend on the filling.
Okay.
Yeah. So, but yeah, looked at half and quarter filling, but since the story seems similar, I would go ahead and say that it should be analogous.
Okay, Dario has also something to add, maybe. Dario.
Yeah, sorry. I mean, actually, I'm retreating a bit what I said before, in the sense that, I mean, I agree that, how can I say, morally, the thing is very similar to the quantum scars regime, but actually, I believe there is, I mean, as you said, it's completely different in some sense. I mean, in the quantum scar typical situation, your system somehow evolves in the sense that, I mean, start to explore several states which are, let's say, orthogonal to your original state, and then come back. Instead here, both your analytical argument and the plot of P of t, show that somehow you are doing a very different mechanism. I mean, you are somehow tuning the interaction such that the evolution doesn't start at all in some sense. I mean, somehow
right.
you do. So
That's
it's a
right.
so if you want, I believe that in the current setup there is no space to analyze the situation in terms of broken Lie algebra, because that is really the game that somehow you do an evolution which explore just a tiny portion of the Hilbert space and come back, you know. So I believe that, yeah, it's completely different. But maybe you could, I mean, if you start to see several states that show this, let's say, avoid evolution in the sense that don't evolve. So maybe if you start to find several states with this feature, you could, how can I say, turn on a very fine-tuned interaction that just make your system jump between these states. Right. And in that way, you could realize something much more similar to the usual quantum scarce setup, in which you start to explore these protected states, and that's it.
Right. Right.
Okay.
Right.
Yeah, it was just a comment. Yeah.
Right. I think you're absolutely right in terms of the characterization difference between scars and this kind of localization. But yeah, I mean, in general, your comment also made me think that there might be something interesting to explore in the critical region where the system is starting to explore more and more of the Hilbert space.
Exactly.
So, yeah.
Exactly. Yeah. Yeah, it's very, yeah, it's an interesting point, probably. Yeah, thank you. Yeah.
Okay, with this, we conclude our seminar. So thank you all for coming, and Sayan, thank you again for this wonderful talk.